Hello and greetings from Dublin, Ireland. My name is A.Cowley and I am a researcher in renewable energy at the National Centre for Plasma Science and Technology at Dublin City University. I will today be presenting some slides on our paper entitled Space-Based Power for Regenerative Atmospheric Geoengineering and Anthropogenic Pollution Control. Firstly, I would like to thank the Space Power Committee and the prize sponsor, Space Canada, for the opportunity to present our concept for a new application of space solar power. We work quite a lot with various types of plasma sources at our faculty, so this idea arose from our experience with atmospheric air plasmas and my interest in space science and renewable technology. One thing we have found after running these atmospheric air plasmas for a period of time, we are always struck by the strong presence of ozone generated from our experiments. As such, we have been interested in the applications of this type of atmospheric modification using plasma jets for some time now. So, the motivation for this paper. Conventionally and culturally, we are exposed to the understanding that carbon dioxide is a greenhouse gas. However, it is by no means the greatest contributor to global warming. Table 1, seen here, illustrates the greenhouse warming potential of many of these other gases. The values are normalized to carbon dioxide as a baseline unit, and we can clearly see that many of these gases have substantially greater impact in terms of the long-term greenhouse effect than conventional greenhouse gases of carbon dioxide and methane. More recently, to address this problem, scientists and engineers have investigated potential technologies for removing or decomposing these compounds into lower value greenhouse warming potential gases or eliminating them altogether via sequestration or decomposition reactions. One demonstrated approach is using plasma discharges. Plasma discharges are electrical discharges that generally will induce ionization, excitation, and dissociation of gaseous pollutants within a targeted region, producing excited molecules, ions, radicals, and thermalized electrons. Many of the high greenhouse warming potential fluoride or chloride compounds present within a diluted atmospheric volume can then be efficiently catalyzed by one or more of the generated reactive species and enter a sequence of reactions that can eventually lead to their decomposition into non-greenhouse contributing compounds or storage molecules. So, this is a potential technological solution. However, the main limiting factor to applying this on a large scale is an energy problem. Namely, it requires a lot of energy to carry this out. Energy which, of course, being produced on Earth would also further contribute to emissions, unless you're using a renewable source itself. In this light, we felt that the space solar concept was uniquely suited to potentially providing energy for such a system, by combining a technology that can induce plasma discharges from space with an abundant energy source provided by the orbiting solar power satellite. We could use this as an approach to help mitigate the effect of these long-term greenhouse gases and also look at generating ozone within specific volumes of our atmosphere. Our approach to use space solar power for beneficial atmospheric modification is as follows. Firstly, we use the space solar power approach as a means of energy generation ex situ of our atmosphere, thus not directly contributing to emissions from the ground. Secondly, we use this power to induce a plasma state at a targeted region of the atmosphere. And thirdly, the regions affected by this ionizing plasma will act as a means of breaking down long-lived greenhouse gases via reaction chains, which can in turn help to mitigate environmental damage. We have identified two potential techniques that could potentially be adapted for this purpose. One is using high-power femtosecond lasers to create a plasma, and the other approach is using high-frequency radiofrequency ionization of the atmosphere itself. Our approach is illustrated in the picture to the right here, showing how a region of pollution could be targeted to help remove fluoride or chloride-based compounds. So, plasma filamentation. In this technique, femtosecond laser pulses in the terawatt power range propagate in the atmosphere. This is due to the competing effect between the optical Kerr effect, which focuses the beam, and the induced plasma effect, which defocuses the beam. This competing effect results in the formation of thin filaments of plasma where efficient nonlinear phenomena can take place. This essentially allows for the propagation of ionizing laser power across much greater distances than would normally be achievable. And you can see in the bottom right here is an image of a terawatt femtosecond laser pulse directed into the sky by students and researchers at the University of Jena. And these pulses were able to traverse up to 20 kilometers in the atmosphere. Our second approach is using high power radio frequency heating of the atmosphere at mesospheric and stratospheric altitudes. This type of technique has already been demonstrated here on Earth by various authors and institutes since the early 50s. Most interesting to our application are the reports of using RF ionization to generate ozone at targeted regions between 22 and 60 kilometers in the atmosphere. So bringing all these concepts together and integrating them onto the classical space solar power approach, when we look at deployment options for these two types of approaches, we can look at modifying existing concepts that have already been discussed within the space-based solar power literature. For example, it would be conceivably simple to modify or append onto an existing Type 1 microwave power satellite the necessary module to carry out the high-frequency radio-frequency ionization approach, thus giving an existing power satellite a dual functionality. Of course, the option remains to design a satellite purely for this approach, but as we've seen before, the return on investment on such dual-use systems tends to be the economically better option. To conclude and summarise briefly, we have presented the concept of how space solar power can be used in a potentially novel way to help mitigate the effect of anthropogenic atmospheric damage and climate change. By using techniques that have already been shown to work on Earth and applying them to the space solar power concept, we have briefly discussed how these techniques can potentially be used in a novel way to mitigate the effects of high residence time greenhouse gases, as well as a means of replenishing ozone within targeted volumes of the atmosphere. By using either the solid-state laser or radio frequency ionization methods, our approach would allow for substantially larger cross-sections of the atmosphere to be targeted that then can be carried out via terrestrial-based projects. Promisingly, in the case of laser-induced plasma filaments, the yield of ozone creation was found to scale in an exponential manner with increasing laser fluence. The scaling up of these type of approaches and its application to the space solar power as discussed could allow for the generation of ozone or the decomposition of greenhouse gases, allowing for the measurable effects on atmospheric composition over macroscopic volumes. To finish, I again would like to thank the competition organisers for this opportunity. I'd also like to thank my colleagues D.Byrne and Dr. N.O'Connor for their discussions and input on this topic. And again, I'd like to thank you, the audience, for your time and attention. Thank you very much.